we're going to talk about how to predict the electrolyte stability window from first principles. Let's dive into that by saying that. So if you have an electrolyte, it has a voltage window where it is stable. And you expect outside of that window, something starts to decompose. So when we say a window, we mean when things start to, or where, at what potential things start at getting reduced, at what potential things start at getting oxidized. So within that, those limitations, you will have an electrochemical stability window. And you can look into it through experiments and computations, and I would say that they are complementing each other to answer questions like which species breaks first, where does it break, and how fast does it break. Okay, so when you are a computational chemist, you are looking into redox potentials in different ways. The thing, or the way that everyone would like to do, is like, okay, I have a structure. That structure is either a molecule or cluster or whatever it is. There is an XYZ coordinates for it. And then I want to do a redox potential on this one using first principles. The first thing is that, okay, I need to have a neutral and an ion structure. So then I will start geometry optimization, then do frequency calculations. And together, I have some information. I want much more better energetics. I go to single point energy calculations, and I will just get information. I have a single point energy, which is sort of the energy that the system has based on the geometry, optimized geometry that we have, plus some correction for thermal or vibrational ZP entropy. So thermal corrections to that energy, and that will give me a Gibbs-free energy for both neutral and ion, either anion or cation. Okay, and then having the difference between these two, some more calculations a bit, I will have my potential, and that potential is an absolute value. If I want, I can find a reference, and for instance, in lithium-ion batteries, we have a reference for it, and we have a referred potential. All these together, they are based on Born-Haber thermodynamic cycle. We should be aware of this thermodynamic cycle. Why? Because there is no chemical reactions happening. Okay, no kinetics here. This is just thermodynamics. And one important thing to add here, that it's not gas phase. We need to consider that we have solvation. Okay, so given that, let's see if it is accurate. If we go through this procedure, we validate this, or everyone has done that. Yes, many people have done that. What we are validated against one of the largest experimental redox data sets of organic molecules. And we do have tested for both oxidation and reduction. So if you see here, we tested it for 150 molecules of that database. And the x-axis is the experimental potential, or half potential, yes, half potential, and the y-axis is our calculated or our predicted ones. Okay, and the diagonal line shows the perfect cases. Okay, each one of those points are one molecule. Okay, so if you look at the statistic on this corner, you would say that they are good. Okay, but I want to draw your attention to this C index, core condense index. It's 0.9. What does it say? It says that if I want to, what does it say? It says that if I want to compare in 9 cases out of 10 cases, it will rank A to be oxidized more than B, or earlier than B, for instance. Okay. Also, the other statistics shows that, you know, it's not perfect, but it's good enough to trust when experimental data doesn't exist. But these are just organic molecules, as I said. But when we move to electrolyte, how is it possible to study those? Okay, if it works. Okay, so when I have an electrolyte, okay, for instance, I do have this LiPF6 in ECDMC as a case. How would I like to study it in using my computer, okay, in computational studies. So there might be different approaches. One we take here in Complar is that we run MD simulations, okay, classical MD simulations. Take it easy, okay, and then we do a thorough molecular dynamics simulation, but testing and validating the force field. We do production, and after that, we have a champion analysis, our very good module, okay, cluster extraction. So we will have solvation shells extracted, so we will have clusters now, and then we tried the DFT redox approach or pipeline on them. We found for those clusters, we found oxidation and reduction potentials, and based on those, we could find the ESV, okay, that stability window that I said. But one thing that I want to remind you here, even in the redox potential, although we had explicit solvation, we added the implicit solvation because we need a background, okay? Let's move forward. And the results are like this. For that electrode that I showed, so we picked, champion picked 36 cluster types, okay? And each line here shows one cluster, okay? And you can see that the reduction limit is this Li plus EC2 DMC. There is no anion in it, okay? So the reduction limit is anion-free, okay? So it's sort of the onset of the SEI formation. So if you move toward the oxidation limit has two double anion in it. So the ESV that we predict here is 6.55 volt. Okay, it's wide. It's wider than people expect. Okay, for instance, this area between 1.5 or between 1 volt to 4 around 4.5 volt, you expect the practical ESW. Okay, but still it works. Okay, I want to remind you, we are in an electrolyte or just electrolyte. It's not a battery. Okay, we are talking about a practical window for batteries. So let's move forward. In a battery, we do have two electrodes which are confining your electrolyte. Okay, so we are trying, and you have an applied potential, and we are trying to do that here. We did some calculations. We tested some confined MD simulations. We got these nice structures, and we showed that on anode, for instance, around in the vicinity of anode, there is just Li free ions. We moved a bit further. We found that anion-free clusters in our structure. I forgot one thing to mention. I switched my electrolyte here. We are working with FEC, EEC, EMC in the persons of LiPF6. Okay, we have a new case here. We are testing if an additive changes things or not as well here. Okay, so if I look at the first or the double layer that I find, there is no anion in it, and I can see that there are different clusters in it. For instance, for one of the clusters, I found the reduction potential is this very small value compared to Li. So it's sort of thermodynamically reducible at that operating voltage. And the voltage that we are applying here are different. In this case, it's 4. Okay, so what we learn here is that the field changes which species are at the surface. And to be more clear here, you can see that if we go from electrode surface to the bulk, you can see that within the 5 angstrom only we have Li free ions. And the further we go, we can see the clusters are being formed, and in the bulk you can see that you will have anion aggregates as well. One thing that I want to draw your attention to is that when in the double layer, in the first layers, you will see that FEC, the additive, is 84% international. So they are enriched by FEC. So it means that you will have the FEC clusters that accepts electrons here, and they break, and they sacrificially form a CI for you in advance of the electrolyte. Okay, and this is very vivid from This is something from the literature. You can see it as well. Yet, we were talking about redox potential. We try to sort of pick a few clusters and test our redox calculations on top of them. If you see here, we tested the clusters for 0 volt and 4 volt in those confined simulations. And you can see, I want to draw your attention to the ESV between the change of ESV between 0 volt cases and 4 volt cases. And you can see that the reduction potential or oxidation potential becomes much lower. So it will just shift things around 2.5, and ESV becomes narrower. So yes, when you go from electrolyte to a confined plus voltage, applied voltage, you can see that it becomes more practical. Again, I want to draw your attention to this practical ESV by Zhu 1 to 4.5. Another thing that I want you to take from this, so you have the same clusters, so chemical formula the same, but the geometry under voltage will be sort of changed, that you end up with different structures and giving you different oxidation potentials vividly. And also this one has a very small positive reduction potential. Okay. So there are many suggestions about, okay, how about not using the redox potentials? Just look at the HOMO-LOMO of the neutral molecule or system or cluster. I think that's a good idea, because on our clusters, the first batch job that we run, almost 40% of the oxidation, geometry optimizations fails. And that's not interesting in terms of cost. So we wanted to look at the HOMO-LOMO of the structures. First of all, it's much cheaper for each cluster. It's 4 to 10 times faster running the simulation. So the customer will not, yeah, it's in favor for the customers as well, or yeah, all of us. And another thing that I want to express here, that okay, the HOMO-LOMO changes if you have clusters in a 0 volt, you have 4 volt clusters, and if you have FEC, let's look at the FEC case here. So it's let me find, this is, if you look at the LOMO here, what HOMO or LOMO change, or how this confinement plus voltage will change things. It pushes the LOMO to deeper areas. So still, it might not give you very good accurate results that you can compare, but it gives the ranking properly, sort of. We learned that before. So what we want to do to mention that, if you have a lot of clusters, you can screen them by HOMO-LOMO, but you need to zoom in and then pick the one cluster that you need to study. And this is what we are still working on, and we want to move and improve it. And finally, I would like to thank you all. First of all, thank my colleagues. And yes, let's get in touch, and we can together make better batteries, I would say. I believe in that. Thanks again.
So if you have any questions, please feel free to write it on the comment, or you can just unmute yourself and ask it directly to Rasul. Okay, so we have a question from Ashley, who's asking, since he missed the first part of the presentation, he wants to know how long does it take to run each calculation cluster. You're muted, Rasul, and
sorry,
you might.
Sorry. I noticed.
Can you please share your screen back again, because we are seeing reflections.
Yes. Okay. Okay. So I would say that if you, for instance, did the whole workflow for this one, depends. But I would say that to produce all these calculations, it took me 1 week. 1 week of everything. However, if you have a very large clusters, the chance to get the results is slower. And ideally, for each clusters, you should be able to get results less than 1 day. for each clusters. I mean, did I answer the question properly? Okay, I can't see you, so you need to say. Yes.
It's also, I think some of our participants are not able to unmute themselves. So maybe, Pawan, you can also write your question on the chat if that's an issue for you. But moving on to the next question. So we have a question from Abdullah, and the question is, what's the main issue that causes 40% convergence failure? Is it the DFT method?
No, it's not the DFT method. Every quantum chemistry code has a criteria that it needs to fulfill to get your structure optimized, and that criteria reaches before sometimes you reach that, you don't reach that criteria within a few cycles that you have started with. Then you need to maximize your increase your cycles. Secondly, I can mention that some you need to change the way that you look into the structure. So the reference wave function, we don't have wave function density, but the reference orbitals that you start, you need to change them. These two mainly causes that. But in the second batch, I could get them almost that 40% reduced to 5% probably, and I could get them in the third, all of them correctly optimized. So it's just a bit a trial and error for some of them, but you can finally get them optimized. Yes, it's not the artifact of DFT. No.
Okay, so thanks. And the next question then is from Pawan, and the question is, when you say DFT, do you mean you've used Gaussian calculations? And also, how do you decide that this is the cluster that you go forward with? So 2 questions.
Okay. Firstly, you can use whatever quantum chemistry code that you have access to. Gaussian is very typical, and but we are not using Gaussian. These data are used with Orca here, but you can use Gaussian if you have access to Gaussian. Yeah. And secondly, the question was that why did I pick those? I didn't for the first. So I let the champion find all clusters, and I did the calculations on top of all. And for the second part, I cherry picked them sort of based on Homo Lomo here. Yes. But generally, ideally, we run them for all.
So the idea here is we first run MD simulation. We get clusters that are categorized and ranked according to the concentration of these clusters that are present in the entire electrolyte solution. And then we pick up the clusters that have the most concentration, or are rather found the most, and the most prone to form a certain structure. And then we look at the Homo Lomo, and those are the clusters that get picked. I hope that answers the question.
Yes, thank you.
And so the next question is, what's the computational capacity required to run this cluster?
What I don't understand exactly what's it, but you need to have access to high performance computing resources if you want to run all of them. But some people, if you just cherry pick, and you can run them on your own computer. So but generally, if you want to study it and all of them as quick as possible, and definitely you need high performance computing resources.
Yeah. Well, we'll be sharing the recording of the screen, and I'll get back to you with whether or not the slides are to be shared or not, but I think we can. And then we have 2 more questions, actually. Yes. So the first one is there any metric to find the stability of electrode materials as well?
No, that's a very good question. And I don't know. I'm not going to answer that question. Feel free if anyone of you knows it. Audience, my colleagues, please.
Well, there's another question then. Yes. So are the MD calculations performed at room temperature?
Yes. These are room temperatures.
But I'd like to add here that the MD calculations are performed at room temperature, but then We also perform constant potential molecular dynamic simulations where we vary the voltage at room temperature again, and that gives us an indication of how the clusters change, and rather how different additives have an effect on the clusters, which in turn decompose on the electrode surface as the voltages vary. So yes, the room temperature remains constant, but then the voltage is varied. So
Yes.
I hope that answers the question. And yeah, so we have another, not question, but yeah, could you reintroduce Compuler broadly? So, yeah, we should have started with introducing Compuler, but I kind of assume that most audience that we have have already been present in the webinar or know us in some extent. So we are a startup out of a spin out of Chalmers University of Technology, and we specialize in providing you first principle physics and chemistry solutions to predict properties of your materials and your electrolytes or any of your liquid formulations. And we use a multi-scale approach where we combine both MD, DFT, as well as certain system level simulations in order to predict certain properties. So using our simulation tools, you are able to screen a wide variety of, or rather a wide variety, as well as a huge number of different formulations that you might have to do physical testing for in a matter of a couple of hours, and sometimes even 1 or 2 days. So yeah, and you can use our software to predict different material or liquid properties or electrolyte properties, such as transport properties, the salt diffusivity, different thermodynamic factors that are involved, different thermodynamic properties, and as well as predict the stability of a system, the redox potential, the electrochemical stability voltage windows, as well as see how your liquid performs at a constant potential when it's confined in a electrical double layer. And we've also recently introduced AI model wherein you are able to predict your conductivity values or ionic conductivity values for a certain set of electrolytes in a matter of few seconds. And we are currently trying to expand this model, not just to fit within the battery industry, but also in a wider material and chemical industry, where you can look into your ionic liquid properties, which, for example, certain conductivity values or diffusivity, or even thermal properties of ionic liquids that are in nature difficult to measure experimentally. You can actually compute them using the software. So yeah, so these are some of the things that we do, but we are constantly growing as well as expanding. So in case you're interested in predicting any of your material properties, please feel free to get in touch with us and write to us, and you can probably find our information at the website, and we'll also share the recording, or you can just simply scan this QR code and reach out to us. Thanks, Russell. But yeah, if there are no more questions, then I think we can wrap it up. And but I would stay for a minute or two here in case if anyone wants to. Oh yeah, so there's one more question. So Shaunak wants to know if it can also be used to analyze additives in a commercial battery. Yes, definitely yes. In fact, we are very proud of the work that we've done there. We have actually used the exact same tool that Rasul shared here of predicting redox potentials for a set of several different additives, wherein the task was the aim was to figure out which additive works best as a CEI, or which additive deposits as an SEI. So for example, which additive reduces first or in turn oxidizes first, and is also able to participate in scavenging reactions, such as scavenging for hydrogen fluoride, as well as form certain desirable polymeric materials. So so for a particular battery manufacturing customer that we have, we screened a set of close to 30 to 40 different additives. First, we use a redox potential approach to figure out the electrochemical stability of all of these additives, and then compare them with respect to each other, and also compare that with a reference additive that we already knew from the customer. And based on these screening, we reduced the number of additives to be tested in the lab from 30 to merely 6 of them. And then these 6 different additives were later on subjected to a very detailed reaction decomposition prediction pathway, where we predicted which of these additives would be a better hydrogen fluoride scavenger, or which of them would produce gassing, or which of them would give us precursors that would lead to gassing, and which one of these additives would then react with all the side reactions that happen as a result of EC decomposing and as a result of certain hydrolysis reaction that gets produced when you have in an electrolyte environment. So yes, we can do, you can actually combine molecular dynamics, DFT, as well as a reaction prediction pathway, including redox, to actually analyze additives for commercial batteries. So we were able to filter down from a pool of different additives into coming up with 3 additives that actually gave us performance, but only one of them was actually selected for was considered by the industry, because that seemed to perform the best compared to the reference that they had. So yes, I hope I have answered that question.
Yes, and they can find information in computationally.com as well. So
yes, and you can also find a white paper on this on our news section. And so the other question is, so you can run a composite study of different additives and electrolytes together, or do you run them separately as their interaction may have different results?
I think we can run them, all of them. So if you have an electrolyte, you give it to us and then you will run it. We don't care how many moieties and molecules you have in there. We can run it, yes.
And so you can run a multi-component electrolyte, doesn't matter how many additives, how many salt it has. And if you want, you can also get an indication of how each one of them affect the interaction by looking at the molecular level species that is generated. So in that way, you know that which of these different components have a more effect on your overall electrolyte properties. So I hope that answers Shaunak's question. Well, are there any more questions? Well, okay, if there are no more questions, then I think, what happened? Can you all hear me?
Yes.
Oh, yeah. Okay. Yeah, okay. Somehow my screen disappeared. Okay, sorry. Yeah, so if there are no more questions, then I think we can conclude this webinar, and we will shortly, oh, okay, there's one more, great. So how expensive is it to run a calculation?
In terms of what?
Well, let's maybe do say it in terms of both the resources as well as I don't know.
The pricing you should consider. You should write to us and ask for it. We can't give you anything, not knowing the thing that you want, but we are confident that we can give you the results as soon as possible. Sometimes in 1 day, 2 days.
So yeah, so if you mean expensive in terms of money, please write to us. We'll get to know, I mean, we need to know what your requirements are, and we have a different pricing for different tiers of customer requirements. Or if you are an academician, if you're in academics, then please write to us. We have different ways in which you can get involved. But if you mean expensive in terms of how much time does it take to finish an MD simulation, then it is 1 to 2 days, depending on what force field we're using. And for DFT, it's a matter of couple of hours. And reactions and predicting reactions could also be a little time consuming, but it will not take you more than a couple of days maximum. Yeah. Okay, well, I think if there are no more questions, then yeah, thanks a lot for all of you to actually join the webinar, and we'll be happy to send you all a recording of it. And if you are interested in knowing more about what we do, please write to us. And if you think there's an application for you to pick out certain aspects of what we do into your own work, please do write to us. And thanks a lot, and it was really happy to see you all, or rather see the names of you all. but yeah, thanks a lot, and have a good day, and hope we can do some more webinars wherein we can have you all again. Thanks.
Thank
Take
you.
care.